Every spring and autumn, the same story plays out in thousands of homes across Britain, Europe, and North America. A heavy storm rolls in. Rain falls for hours. Water pools around the foundations. Within a day or two, the basement or cellar starts to smell damp. Then come the dark patches on the walls. Soon the carpet is ruined, the boxes of old photos are ruined, and the dehumidifier is running day and night. Homeowners call plumbers, dig up the garden, install French drains or sump pumps, and still the problem returns the next big storm. Modern building science tells us this is normal. Concrete foundations, impermeable membranes, and compacted soil create hydrostatic pressure that pushes water inward. We treat the symptom with pumps and plastic, but the root cause, poor drainage at the foundation level, remains. What if our ancestors had already solved this problem hundreds of years ago? They had. The solution was simple, cheap, effective, and built to last centuries without electricity or maintenance. It was called a rubble drain, or stone drain, rubble-filled trench, or gravel channel. Medieval builders used it around castles, monasteries, farmhouses, and townhouses. They dug trenches, filled them with loose stone and rubble, and let gravity and natural permeability do the work. Water flowed away from the walls instead of pressing against them. These systems survived wars, floods, and centuries of use. Many are still functional today when archaeologists uncover them. This is the story of the rubble drain, how it was built, why it worked so well, why we abandoned it, and what it can still teach us about keeping water out of our homes in an age of heavier storms and changing weather patterns. By the end of this exploration, you will understand not just a forgotten technique, but a completely different way of thinking about foundations, water, and buildings that breathe. Walk into any modern house with a basement after a storm, and you will see the symptoms of poor drainage. Water enters through cracks in the foundation, through the joint between the wall and floor, or by rising through the slab itself. The usual culprits are easy to name. Impermeable concrete and waterproof membranes trap water against the walls. Compacted soil and poor grading around the house direct rainwater straight to the foundation. Gutters and downpipes that empty too close to the walls. Rising groundwater during prolonged wet periods. Climate change bringing more intense rainfall events. The standard modern fix is often expensive and energy dependent. Exterior excavation, new French drains with perforated pipe wrapped in geotextile fabric, sump pumps, interior waterproofing coatings, and dehumidifiers. These solutions can work, but they treat the symptom rather than redesigning the relationship between the building and the water around it. They are also relatively new in the long history of construction. Our medieval predecessors faced the same problem of water near foundations. They did not have plastic membranes, electric pumps, or concrete. They had stone, clay, timber, and a deep understanding of how water moves through the ground. Their solution was elegant in its simplicity. A rubble drain is a subsurface drainage channel created by digging a trench and filling it with loose stones, rubble, gravel, or broken masonry. Sometimes a larger stone or a row of flat stones formed a crude channel at the bottom. The trench was usually sloped gently to carry water away from the building to a lower outlet, a ditch, a stream, or porous ground. Key characteristics that made it different from modern pipe systems. It was permeable throughout. Water could enter from the sides and top as well as flow along the bottom. It did not rely on a single pipe that could clog. The loose fill allowed air and some movement, preventing the complete sealing that happens with modern impermeable membranes. It was often self-maintaining to a degree because fine silt could pass through or settle without blocking the entire flow path. Construction used locally available materials, broken stone from the building site itself, field rubble, or gravel from nearby pits. In essence, a rubble drain created a highly permeable zone that lowered the water table immediately around the foundation and directed excess water away by gravity. It worked with the physics of water movement rather than fighting against it. Drainage systems using stone and rubble date back thousands of years. Archaeological evidence shows simple stone-lined or rubble-filled channels in Roman Britain, and even earlier in some parts of Europe for agricultural field drainage. By the medieval period, roughly 5th to 15th centuries, the technique was widespread and refined for buildings. In Britain, rubble drains appear in excavations of monastic sites, castles, and townhouses. Monasteries in particular needed reliable drainage for their complex water systems, supplying clean water while removing waste and stormwater. Castles with deep cellars and undercrofts faced constant challenges from groundwater and rainwater running off high walls. One well-documented example comes from Exeter in England, where medieval drains have been traced through the city. These were often stone-built channels or rubble-filled trenches that carried water away from buildings and streets. Similar systems have been found at sites across England, Scotland, and parts of continental Europe. The technique was not limited to grand buildings. Ordinary farmhouses and village homes used rubble drains around foundations and in yards. Agricultural field drainage also relied heavily on rubble and stone-filled trenches, long before the invention of clay tiles or perforated pipes in the 18th and 19th centuries. Henry French's famous 1860 book, Farm Drainage, popularized tile drainage in America and helped spread the modern French drain concept. But the rubble version he built upon was already ancient. French farmers had used modified clay roofing tiles and trenches as early as the medieval period, and stone/rubble systems were older still. Archaeological evidence and surviving examples allow us to reconstruct the typical process. Step 1. Site assessment and planning. Builders observed where water naturally collected or flowed after rain. They noted the slope of the ground, the height of the water table, and the type of soil. Clay soils needed different treatment than sandy or gravelly ones. Step 2. Excavation. A trench was dug around the perimeter of the building or along the line where water needed to be intercepted. Depth varied, often 1 to 2 meters or more, reaching below the foundation level or into permeable strata. Width was typically 30 to 60 centimeters or wider, depending on expected water volume. Step 3. Base preparation. Sometimes the bottom of the trench was lined with flat stones or a layer of larger rubble to create a defined flow path. In other cases, the trench bottom was simply left as dug if the subsoil was already reasonably permeable. Step 4. Filling with rubble. The trench was filled with broken stone, field rubble, gravel, or fragments of building stone. The fill was usually placed in layers and sometimes lightly compacted, but not so tightly that it became impermeable. Larger stones at the bottom graded to smaller material higher up in some designs. The goal was maximum void space for water to flow while still providing structural support. Step 5. Covering and backfilling. The top of the rubble was often covered with flat stones, turf, or a layer of clay or soil to prevent surface debris from washing in too quickly. In some building contexts, the trench was backfilled and the ground surface restored or landscaped. Step 6. Outlet. The drain needed an outlet at a lower point, into a ditch, a stream, a soakaway, a pit filled with rubble for dispersal, or simply into more permeable ground downslope. Variations existed. Some rubble drains incorporated a central stone channel or a line of hollowed stones. Others were combined with clay-lined channels for more controlled flow. In monastic complexes, multiple rubble drains might feed into larger stone-built sewers. The beauty of the system lay in its adaptability. Local materials, local knowledge of the land, and simple tools were all that was required. No imported pipes, no specialized factories, no ongoing energy input. Water moves through the ground according to gravity, pressure, and the permeability of the soil. Modern concrete foundations and impermeable membranes often create a barrier that forces water to build up pressure against the wall, hydrostatic pressure. This pressure pushes water through any crack or joint. A rubble drain changed the equation by creating a zone of very high permeability right next to the foundation. Water entering the rubble could flow freely downward and away, instead of pressing sideways against the wall. The loose fill also reduced capillary rise, the tendency of water to climb through fine pores in soil or masonry. Because the system was open and permeable throughout its length, it could handle varying volumes of water. During a heavy storm, it carried large flows. During drier periods, it still allowed some air movement and prevented complete waterlogging. Unlike a single perforated pipe, common in modern French drains, a rubble drain had thousands of small pathways. If one area silted up, water could find another route. This made the system more resilient over decades or centuries. Archaeologists have noted that many medieval rubble drains are still partially functional centuries later when uncovered. The stones have settled, but the basic permeability remains. Modern pipe systems, by contrast, often require cleaning or replacement after 20 to 50 years because of clogging or root intrusion. Excavations across Britain and Europe have revealed rubble drains in many contexts. Monastic sites frequently show sophisticated drainage networks combining stone channels and rubble-filled trenches. These protected cellars, kitchens, and infirmaries. Castles and fortified houses used rubble drains around curtain walls and undercrofts to keep defensive spaces dry. Townhouses in places like Exeter and other medieval settlements had perimeter drains to protect cellars used for storage. Agricultural contexts show rubble drains in fields and around farm buildings, the direct ancestors of later tile drainage systems. Some surviving examples in old buildings still function when modern owners rediscover and maintain them. One striking aspect is how often these drains were built using waste material from the construction itself: broken stone, offcuts, and rubble. Nothing was wasted, and the drain became part of the building's own fabric. In some cases, rubble drains were combined with other traditional techniques such as lime-based mortars and breathable walls. The entire building envelope was designed to manage moisture rather than seal it out completely. Rubble drains succeeded for hundreds of years because they aligned with fundamental principles. They used gravity and natural materials. They were repairable and adaptable. They did not create the sealed, pressurized environments that modern impermeable systems often produce. Maintenance was minimal. Occasional clearing of the outlet was usually enough. They worked with the local geology rather than against it. When storms came, the water had somewhere to go. When the ground dried, the system still allowed some ventilation. The building and its surroundings existed in a dynamic balance with water, rather than in constant opposition to it. The Industrial Revolution and the rise of modern building science changed everything. Mass-produced clay tiles, then concrete pipes, then plastic perforated pipes became cheap and standardized. Building codes increasingly favored impermeable membranes and mechanical solutions. The idea of a breathable foundation gave way to the ideal of a completely dry, sealed basement. By the 19th and 20th centuries, rubble drains were seen as primitive. New houses were built with concrete foundations and often no perimeter drainage at all, or with minimal pipe systems that were easier to install but less resilient. The knowledge of how to build effective rubble drains faded from mainstream construction practice. Today, we are rediscovering the costs of that shift. Basements flood more frequently in many areas. Repair bills are high. Energy is consumed running pumps and dehumidifiers. The environmental footprint of modern drainage materials and their eventual replacement is significant. Climate change is making the problem worse. More intense rainfall events overwhelm systems designed for milder conditions. Older buildings with traditional drainage sometimes perform better than newer ones with modern but poorly maintained piped systems. The Rubble drain offers several practical lessons for contemporary building and renovation. 1. Permeability over impermeability at foundation level. Allowing water to move away through a permeable zone is often more effective than trying to seal it out completely. 2. Gravity-fed systems are robust systems that rely on simple slopes and natural flow, need no electricity, and have fewer failure points than pumped systems. 3. Local materials reduce cost and environmental impact. Using rubble or gravel from the site or nearby sources is cheaper and lower carbon than importing plastic pipes and geotextiles. 4. Resilience through redundancy. Multiple small pathways are more forgiving than a single pipe that can clog. 5. Integration with the landscape. Good drainage works with the natural slope and soil conditions rather than fighting them. Modern sustainable drainage systems, SUDs, in the UK, and similar approaches elsewhere are beginning to rediscover some of these principles. Permeable paving, rain gardens, and gravel-filled trenches are once again being used around buildings. The Rubble drain is essentially an early, low-tech version of these ideas. If you own an older property or are building new and want to apply these lessons, here is a practical modern interpretation. Materials: excavated trench, clean angular stone or rubble. Avoid very fine material that can wash away. Optional: larger flat stones for a base channel. Optional: geotextile fabric on the sides and top. Modern addition for longevity: outlet pipe or open channel to a suitable discharge point. Steps 1. Assess the site and determine the best route and outlet. 2. Dig a trench at least 30 to 50 centimeters wide and deep enough to reach below the damp-proof course or foundation level, sloping gently away from the building, minimum 1 to 100 fall. 3. Place larger stones or a row of flat stones at the bottom if desired. 4. Fill the trench with rubble or gravel, layering and lightly compacting as you go. Leave plenty of void space. 5. Cover the top with geotextile, optional, and backfill with soil or turf. 6. Ensure the outlet is clear and directs water safely away into a ditch, soakaway, or lower ground. 7. Consider combining with improved surface drainage. French drains can be paired with regrading the ground, extending downpipes, and adding permeable surfaces. For existing buildings with flooding problems, a perimeter rubble drain combined with internal breathable lime plaster or improved ventilation can often solve issues without full excavation and tanking. Lower long-term maintenance when properly built. Better handling of variable water volumes. Lower embodied carbon if local materials are used. Compatibility with breathable traditional building materials. Resilience to minor silting or root intrusion. Often cheaper to install on sites with easy access to stone. Modern perforated pipe systems have advantages too. Easier to install in some situations, more predictable flow rates, and compatibility with current building regulations. The best approach in many cases is a hybrid, using rubble or gravel principles where appropriate and modern materials where they add value. Historical examples show rubble drains lasting 200 to 800 years in some cases. When uncovered by archaeologists, many still show evidence of water flow paths. In modern contexts, homeowners who have installed gravel or rubble-style perimeter drains around older properties often report dramatic reductions in basement dampness. The systems handle heavy rain events better than expected because water can enter from a wide area rather than being funneled into a single pipe. One common observation: Properties with traditional rubble or stone drainage that was never completely removed sometimes perform better during extreme weather than neighboring houses with newer but clogged or poorly designed pipe systems. Do rubble drains clog? They can silt up over very long periods, but the multiple pathways make them more tolerant than single pipes. Occasional maintenance of the outlet is usually sufficient. Are they suitable for all soil types? They work best in soils that allow some lateral movement of water. In heavy clay, they may need to be deeper or combined with other measures. Can I combine them with modern waterproofing? Yes. Many successful modern installations use a rubble/gravel zone outside a breathable or partially permeable membrane. What about health and mold? By reducing water pressure against the walls, rubble drains often lower internal humidity and mold risk more effectively than sealing alone. Is this just an old French drain? The French drain concept, popularized in the 19th century, built directly on earlier rubble and stone drainage traditions. The rubble version is the older, lower-tech ancestor. As storms become more intense and sea levels rise in some areas, the ability of buildings to manage water without constant mechanical intervention becomes increasingly valuable. Rubble drains represent a low-energy, high-resilience approach that aligns with principles of regenerative and sustainable design. They also remind us that much of what we consider modern problems, damp basements, flooding, poor indoor air quality, were addressed by builders who worked with natural materials and observed how water actually behaves in the landscape. The medieval rubble drain is not a magic solution for every situation, but it is a powerful reminder that effective drainage does not always require complex technology. Sometimes the answer lies in creating space for water to move naturally, using simple materials, and designing with rather than against the forces of nature. The next time heavy rain threatens to turn your basement into a swimming pool, remember that people hundreds of years ago faced the same challenge and solved it with trenches full of stones. Their solution was not high-tech, but it was deeply intelligent. It lasted for centuries. It used what was available locally. It worked with gravity and permeability instead of fighting them. We do not need to abandon every modern material or method, but we can learn from the rubble drain's core principles, create permeable zones, respect natural water movement, use robust and repairable systems, and design buildings that can handle the weather rather than assuming the weather will always be moderate. The medieval rubble drain was the answer to the basement that floods every storm. It still has lessons for us today, lessons about resilience, simplicity, and living with water instead of constantly battling it. If this exploration of forgotten building techniques has changed how you see the ground around your house, consider looking more closely the next time it rains. Watch where the water goes. Notice the slope of the land. Think about what a simple trench of stones might achieve. There is a great deal of practical wisdom still buried in the ground, literally. The rubble drain is just one example. Subscribe if you want more investigations into the building methods our ancestors used that modern engineering has quietly walked away from. The next forgotten technique might be the one that solves a problem in your own home. Thank you for reading. Stay dry, and remember that sometimes the oldest solutions are still the smartest.